Hello everyone. A small metal ball is being pulled gradually on a fixed frictionless sphere. Friction is not absent, friction is not present, and the hemisphere that we can see in the diagram is fixed. Radii of the ball and that of the pulley are much smaller than that of the sphere. This ball can be taken as a point size ball. As the ball slides from the bottom to the position close to the top of the sphere, the ball gradually moves like this from the bottom near the top. So we have to check the options. Achha, capital R is the contact reaction, normal reaction force between the ball and the hemisphere. So options we have to check whether F increases or R decreases, F decreases and R increases, F decreases and R remains unchanged, or F remains unchanged and R decreases. So this is a very nice problem from the book Pathfinder. So let's try to solve it. So if we draw the diagram, this is the hemisphere and after certain instant, let us say the ball reaches some position here. The center of the sphere is here. So if I draw a line, a vertical line, it will meet the pulley somewhere, and the height of the pulley from this ground is fixed. So let us call this height as h. Also, the length of the string connecting the ball to the pulley, we are talking about this length. Let us call this length as x. This is continuously decreasing as the ball is moving from bottom to the top. Also, the radius of the sphere, radius of the hemisphere is fixed. Call it small r. Now, what are the forces acting? The forces acting are the normal reaction like this. Here we have to take it as R. The weight of the ball mg, and since it is an ideal string, the same force F will act like this. Now F is acting along the length x, R is acting along the radius r, the capital R, and mg is acting along the height h. Now here we can write sine rule sine rule for the triangle. Let us say this angle is theta 1, this angle is theta 2, and this angle is theta 3. So if we take the distance triangle, then we can write small r upon sine theta 1 will be equal to small h upon sine theta 2, and this can be written as x upon sine theta 3. Also, we can replace the distances by the forces. Since the body is gradually being pulled, so we can say that the speed of the body at any instant is 0. Also, the acceleration of the body at any instant is 0. So the condition satisfies equilibrium condition of the body. So the body is under equilibrium, and that is why we are able to apply sine rule or Lami's theorem. So if I replace the length of the sides by this force vectors, then we can do it because the body is under equilibrium. So small r can be replaced by capital R. So r upon sine theta 1, or this should be equal to, along h mg is acting, so we can write mg upon sine theta 2, and along x we have f, so f upon sine theta 3. And from equations 1 and 2 we can write that r upon small r should be equal to h upon mg should be equal to f upon x. So call this equation number 3, and this value is a constant, some constant this value is. Now we can see that here we have r as a constant, small r is a constant. So this implies capital R remains unchanged. Remains unchanged. So we got the condition on capital R. So the normal reaction capital R remains unchanged, so that this ratio R by R remains constant. Also, small h is a constant, mg is a constant. So from there only we got this value as a constant, because h and mg are constant. They are known quantities. Also, for f by x to remain constant, since x is continuously decreasing as the ball moves from the bottom to the top of the hemisphere, the value of x continuously decreases. If x decreases, to keep the ratio constant, f should also decrease. So f decreases. So our correct option should contain R remains unchanged and f decreases. So the correct option is C here. So that is the solution to this problem. Thank you very much.